Hello, this is Mesos Orm and welcome to SFML Tutorials. Today we'll be looking at Worley and Voronoi noise. First, for ease of use, we're going to make a float for our width and height. We're going to say float, w float, and that will equal a float version of our width. Now we can copy this, paste it here, say h float, then say height. Now we need to make a vertex array. We should say SF, vertex array, verts. Now we should set the primitive type to triangle fan. So we'll say verts dot set primitive type to SF, primitive type, triangle fan. We will need 5 positions, so we will say verts dot resize and 5. Now our first position is at 0, 0. We'll say vert 0 dot position is equal to 0.0f by 0.0f. Now we will copy this and paste it 4 times. Then we will change this to a 1, a 2, a 3, and a 4. This will become w float. This will become w float as well. And this will become h float. And this will also become h float. We may copy the 0 position and paste it down here because they're exactly the same. Now we can save and scroll down. Now we're going to need a shader, SF shader, shader. Later on we'll need our mouse position, so we'll say SF vector2i pixel position, and this will equal SF mouse get position relative to the window. Now for our mouse position itself, SF vector2f mouse position, which will equal window dot map pixel to coordinates and pixel position. We will need to change our mouse position to clip space, so we will say mouse position equals mouse position dot component wise divide, and inside of here we will say w float by h float. Now we may draw the vertices to the screen, so we will say window dot draw verts, and then we will reference our shader. In our resource files we will say add new item. Then we will say Voronoi.vart. We will also make a similar file for our fragment shader. Now we will go back to our vertex shader. We will say sharp version 460 compatibility. We will need the size of our screen, so we will say uniform vec2 high resolution. We will send our position to the fragment shader, so we will say out vec2 position. Now we can say void main and encapsulate that. For anyone that wants to use a texture, we can say vec4 text chord equals gl texture matrix add 0, and then multiply that by gl multi text chord 0. We will need to retrieve our vertices, so we will say vec4 vertex, which will equal gl model view projection matrix multiplied by gl vertex. Now our position will equal our gl vertex dot xy divided by our I resolution dot xy. Now we can say gl position will equal our vertex. Also, gl text chord add 0 will equal our text chord. Lastly, our gl front color will equal gl color. Now we can save and then go into the fragment shader. Here we will say sharp version 460 core. We will take in our vec2 position and also have a uniform vec2 mouse position. Down here we will say void main, and up here we will make a function void main image. It will take out a vec4 fragment color and in a vec2 fragment chord. Copying this, we'll paste it down here. Inside, we will say gl fragment color as well as GL fragment chord.xy. Back in main image, we will say vec2 uv equals our position, as well as vec3 color equals vec3 0.0. Now first we're going to make Worley noise, but both need points, so we will say const int num points equals 8. Now we're going to make a vec2 array of our points, vec2 points, inside of here num points. Now we're going to fill out that array. And this last point will be our mouse position. Let's scroll down a bit to give us room. We will need to know our final minimum distance from our current UV to a point, so we will say float min distance equals 1.0. It is set at 1.0 because that is the highest possible and we will only be taking away from it from now on. Now we can make a for loop, say for int I equals 0, I is less than num points, then plus plus I. In here, we'll want to know the distance between our current point and our current UV, so we will say float distance equals distance between UV and points at I. Now we can set our minimum distance. We will say min distance equals min of our min distance by our distance. Outside of the for loop, we will say color equals vec3 of our min distance. Then our fragment color will equal vec4 of our color and 1. Saving this and going back to main, here we will say if not shader dot load from file. In here we will say Voronoi dot vert, copy that. Down here, standard CERR error could not load shaders. Now we can scroll down, go down here. We will say shader dot set uniform I resolution. And here we will say SF vector2f, and we will copy this, paste it here. We will also say shader dot set uniform mouse position, and then we will put in our mouse position. We can go back into our fragment shader, and then we can enter the debug menu. Now from there we can make Voronoi noise. We can say vec2 min point. Now if we go down here, cut this out, say if our distance is less than our min distance, then our min distance equals our distance, and our min point equals our points at I. Now we can go down here, say color.gb equals min point. Now we can finally enter the debug menu and see that our Voronoi noise works. Now, if we want a random distribution of points, we can make a random function. We will call it vec2 random2, and inside of here we will say vec2 u and encapsulate that. Here we will say float a equals the dot product between u and the vec2 of 127.1 by 311.7. Then float b equals the dot product between u and vec2 of 269.5 and 183.3. Then we will return the fractional part of our sign of vec2 between a and b multiplied by 43758.54 5.3. Now we can save and scroll down. Now we're going to cut this out. We are going to tile our space. To get the tile coordinates of the UV, we will say vec2 I UV equals floor of UV. Then to get the UV coordinates in that tile, we will say vec2 FUV equals the fractional part of our UV. We will be changing our for loop between -1, less than or equal to 1. Then we will copy this, paste it down here, encapsulate all of this, make this go over here. Then we will say int j equals -1, j is less than or equal to 1, plus j. These for loops will iterate between the 8 adjoining cells around our current cell. To get our current cell's neighbor, we will say vec2 neighbor equals vec2 float I float j. To get the point we will be checking our distance to, we will say vec2 point equals I UV plus our neighbor. We will need the difference between our current point and our neighbor's point, so we will say vec2 difference equals our neighbor plus our point minus FUV. Now our distance will be the length of our difference. Finally, we will change this to point instead of points. Now we're going to save. Before we open the debug menu, we're going to take out the mouse position on both sides, go back to the fragment shader. Then we can open the debug menu and see that there's nothing here right now because we need to zoom out. So we're going to scroll up, go here. Then we will say UV times equals 12.0. We will save that and open the debug menu and see that it's still not working because we need to do one more thing. Down here, around our point, we need to say random 2 and encapsulate that. We will save again and open the debug menu and see that our Voronoi noise works again. Now we can scroll down, change this to RB to give us a little better of a look. Know that we may use different distance functions, so we can say absolute of our difference of x plus absolute of our difference dot y, this being the Manhattan distance. This is also called taxi cab distance or city block distance, where instead of taking the shortest length between 2 points, you would instead take the length of travel along a grid. Saving, and then opening the debug menu, we can see that we get an entirely different type of Voronoi noise. We can also do something called chessboard distance, where we would take the max of this. We'll save, and then open the debug menu, and see that it's also very different. Thank you for joining me today. If you did, then please like, comment, and subscribe, and have a great day.